Hey guys, this is Eric Weingartner with Weingartner Racing for a technical video for you today. This one's about exhaust flow. This one's probably going to be a little bit hard to explain everything, and some of you probably want more definitions and more details, and some of you are like, well, this is going way over my head. I'm trying to shoot in between. If I made the video in depth to the degree that some of you want, the video would be extremely long. And one of my favorite movies is Heat, and there's a line in there that says, don't waste my mother effing time, and I don't want to waste your time. The other one of you will be like, I don't understand, this is too complex. I'm trying to shoot for the in-between and give you as much information as possible, but it's about exhaust flow. And I'm going to do some tests, and I think you'd be interested to hear what's going to happen in this video. So I'm going to tell you, I'm going to give you information about exhaust flow. I'm going to flow this head, which has already been done before. This is the KMJ Assault head for a small block Chevy that I just used for this test. But in reality, I could have used a Ford head or any other head, big block head. But this one fits the purpose for this test easiest, and you'll see as I go through some of the tests. So don't think it only applies to small block Chevy. It really applies to LS and everything else. Anyway, so I'm using this for the test. What I'm going to do is I'm going to flow it, and I'm going to flow it with 3 different valves here. This is a 45-degree seat, and every one of these exhaust valves are 45-degree seats. They're just different in slight ways. I'm going to flow it in the normal direction, so as exhaust gas would go out, and then I'm going to flow it in reverse as if reversion was happening, because the reversion does happen in several systems. So we're going to do it that. Then I'm going to flow it with an exhaust pipe attached, and I'm going to use it in different directions. Then I'm going to put a bigger exhaust pipe on it and see how that affects flow. So that's what's happening in this video. But before I do this, let me explain some things about flow bench and exhaust ports. The flow bench really just becomes a tool for exhaust ports, because the flow bench does a much better job of giving me some information about the intake ports, but on the exhaust port it gives me very little. It gives me a small amount, and some of you would argue against that, but my defense to this is, in a live engine there's way more pressure on the exhaust than there is on the intake side, and the flow bench can get closer to matching the flow characteristics on the intake side than it can the exhaust. Because of this, the flow bench can in some ways lead you wrong if you were to design exhaust ports. But it does give you information. You just need to know how to use it, but it's not the end all. And I'll show throughout this video what I mean by it. It's a useful tool, but it's definitely not the most important thing. It does a better job of guiding you on the intake port than it ever does the exhaust port. Anyway, but there's some major things you need to know about exhaust flow before I can ever show what's going to happen in test. So let me try to explain for you. Okay, so the first thing to try to explain about the exhaust port is, it seems like it's not that important, but it's very important for engine performance, both NA and supercharged or turbo applications. And the reason why, and I'm trying to make this general, so just bear with me. The reason why is because the way the air flows or moves in an engine, it goes from high pressure areas to low pressure and vice versa. So if you think about it, a lot of people think that just when the piston starts coming down, that's when it's drawing air from the intake valve. That's actually not true. It actually starts long before that. And if you're like, I don't believe you, I would say, okay, then when you go to degree or cam, why is the intake valve open before the piston starts moving down the hole? And there's a reason for it. So here's what's happening in the engine. So air draws in, of course, gets compressed, and then there's an explosion that happens and the piston starts moving down. Well, when that explosion happens, or when the fuel's ignited, what happens is it's creating a high pressure area in the port. And then the exhaust valve opens and that high pressure gas leaves. Well, that high pressure gas leaving creates a low pressure here inside the cylinder while the piston's still on its way up. As it's towards the top, I should say. The exhaust leaving high pressure, leaving a low pressure point behind. So at this time, usually when the valves get about here, this is called overlap, we open the intake valve because there's a low pressure created here because the exhaust pressure is out that way, high pressure creating a low pressure here because there's less gas there. And that low pressure will cause the air to be pulled from the intake valve first. And then we close the exhaust valve and the piston starts drawing more. That's how your beginning part starts. This is the reason why having a cam timing is so important. Because if you leave the exhaust valve open too long, that high pressure is left, and now it's creating low pressure, and the low pressure starts coming up here, and it'll actually start drawing some of the incoming air from here into your exhaust port. But it also, if you close it, if you don't have it open long enough, you end up having a high pressure still inside the cylinder itself. And when you open the intake valve, that high pressure goes back up and you've got reversion on the intake side. And there's some other things that can cause this as well. But again, I'm just being general. If it helps you to know a visual representation of this, here's a good one to look at. Go watch the video of the atomic bomb being exploded, and when they show like the tree line. What you'll see is you have an explosion, obviously the nuclear explosion, and the heat starts radiating out, so you have a pressure wave expanding out from the explosion, and then you see the tree literally wave this way. And what that happens is when that expansion happens, that creates a low pressure where the atomic bomb had gone off. So you see the tree hitting this way from the expansion wave, and then you see the low pressure created because all that expansion has happened. There's a low pressure, and you see the reverse happen. That same thing happens inside of a cylinder every time there's a cycle. The gas expands, out it goes, low pressure is created, and it might come back, hence reversion. So our goal for this, whenever we try to design exhaust ports, is we want it where the gas is easier to get out, harder to get back. So hopefully that gives you some guidance on what I'm talking about. But the biggest thing is having the overlap, that's the part where the cam and both are open at some point. Getting this timed right is so critical. So if you have a good cam guy, they can figure this stuff out. And by the way, I'm going to go ahead and do a little offshoot here about cam guys. There are some really good ones out there, and then there's some ones that claim to be good that aren't good. So I do spec custom camshafts, and there's some guys that I think that are even more, very talented, more so than ever I could be. And if you're ever wanting a recommendation, I'd be happy to give you mine, and I sell them. But if you're like someone else that I would be involved with that I've used before, and if there's something that's beyond my realm of knowledge, that person would be Mike Jones. He does a great job, and I really trust his opinion, and I think he's a good cam guy. There's several others, like Cam Motion I think is good. Brian Tooley does a good job with the LS stuff too. These guys understand what's happening at these points and able to design a camshaft that works with what you want. But I will point this out too. No matter how good your cam guy is, they get you the best cam that they think will work with what you're doing. I promise you, in 3 more camshafts, you can find a better one. And that's because they'll know what they've got now, have a baseline, they could change things to make things better, period. So if your cam guy's telling you this camshaft's gonna be the best you'll ever have, nothing else, they're lying. It just gives you the closest they think, and from using 2 others, they can probably get you a better one. But no one wants to spend $1,200 in camshafts and the time to do that. So anyway, there you go. So that's the beginning of how this exhaust thing's so important. So what's this do with our exhaust test today? Well, today we've got the 3 valves here. Now these are all different in slight ways. Being that they're all 45 seats, let's switch them the right way. We can go over it. This is a nail head, which we talked about in a previous video. It means it's flatter here. This is, which was 45, no back cut. This is a nail head design, but with a back cut. It's got a 30 degree on it from the factory. This is a tulip exhaust valve. It has no back cut, still 45 degrees. Each one will be flowed in forward direction, as in the exhaust gas is leaving. Then acting as reverse, we'll suck it in and we'll see what happens. We'll see how they change across the board. And hopefully that'll explain why I no longer use back cuts on the exhaust valves, unless the valve just came that way. So we're going to do that, and then I'll flow it with the exhaust pipe, because several companies advertise flow numbers with exhaust pipes. I do not, because I think they're pointless, and I'll explain why later on in the video. All right, guys, let's get started with some testing. Okay, before I begin the flow test, while I was hooking up the head, I got to thinking I better clarify my statement about the camshafts. I think if you give the camshaft guys all your information, in the very first camshaft, they'll probably get you a camshaft that's about 80% of what the best camshaft could ever be. Some people will get closer because they've got more experience, or they've been doing it longer in some ways, or whatever, have more knowledge on how to pick a better camshaft. But anyway, after that one, if you send them your data and they look at it, they'll be like, whoa, okay, it looks like I could probably add a few more degrees of duration here or there, or I can move my intake opening or exhaust closing in some way, and I bet you I can get you just a little bit more. And then they would get you another camshaft, and then 3 more camshafts will probably get you pretty close to 95% of where the best camshaft would be. The next 5% is going to take considerably more because you're looking at smaller gains as you go on. So I wanted to clarify that statement beforehand, before someone hits me with a bunch of comments. But anyway, to the testing. So here's how it's going to work. I'm actually recording me while I'm testing this so that you could actually hear the exhaust ports, because their tone will probably change for each valve. That's one thing that the FlowBench can kind of tell you. What you should hear is as the valve opens, it should get quieter. And you might say, why? Well, typically we want the throats to be somewhat bigger, but we don't really care about the low lift flow. And someone's gonna be like, oh, yes you do. Not really, because you'll see, it's gonna make things worse for reversion. But as the valve comes open, the port itself should get quieter. So you should hear it get quieter. But anyway, we're gonna hear the differences on each one of these, and we'll talk about them. So here's the other thing. I'm only gonna flow to 7/10 of an inch of valve lift. And the reason for that is because usually I go all the way to 1 inch, but I'm trying to make the test quicker, so you're not watching a ton of just flowing of heads. So this first one is the nail head valve, 45-degree seat, no back cut. I'm gonna start the test and we'll go ahead and get this ball rolling and you get to enjoy it, hopefully. All right, let me move the camera so you can see the flow numbers. Alrighty, hopefully this captures it correctly. They'll be up on the screen right in front of you. All right, I put on my ear protection. Going 1 to 700 in a 1/10 of an inch increment. Someone's gonna say, why don't you go 50 thousandths increments? Because I don't have the time. Okay, so I just got done flowing this, and you can see the flow numbers up here, but I am gonna do a print off sheet. I'm just kind of showing you. I won't do this on each, I'll flow each of the other ones and let you hear it and see the numbers, but I'm just showing you this one here. So you can see what it's done. Now, by the way, if you're watching here, when it was doing it, if you watch up here in this area, it'll say, hey, you're taking readings. Well, it's taking 15, I think it is, and it averaged those and puts them here. It kind of takes away some of the variance between electrical flow coming in and little stuff like that. Okay, so anyway, there's that. First one down, this is the nail head, 45-degree, no back cut. Next one's gonna be nail head, 45-degree, 30-degree back cut. All right, let's do that next. Okay, this is the next test. I'm just gonna show you this beforehand. You see this line here? This is the first one. What you'll start seeing is a red line popping up here, and if it's below, then it's flowing before, so you can see the curve changing. All right, I'm gonna go ahead and do this one. See if I can get my camera right for you guys. I don't know if it'll help you out or nothing. I have no idea how it looks to you guys. But anyway, let's go. right, that one's done. You can see the graph. The red line's what it is now. That's with a 30 degree. I'll show you the raw numbers later, I promise. All right, on next test, the tulip exhaust valve. Okay, next test. This is the tulip exhaust valve. Let me get the camera right there. All right, here we go. There's that. And then for those that are, I will print off this and talk about it later on, but let's close this out. If we do report, make report, there's your exhaust numbers, which I'm gonna print this out because I know there's a glare from the LEDs above. But anyway, there, so you can kind of see, which we'll talk about in a minute. Okay, now so far this has all been flowed in the normal direction. So let me go over the thing. This means the air is being pushed out the exhaust port here. What I'm gonna do is I'm gonna turn the direction and make it suck in. Now usually when we're flowing intake ports, we'll put Clair on it, but for the sake of time and to keep everything uniform, I'm not doing that. I'm just gonna have it suck this way. So, and then we'll see which one flows better in reverse and go from there. All right, here we go. Okay guys, here's the results, and I'll explain this. You just saw me running the test, but what you didn't see me do is flowing in reverse, which would be sucking the exhaust port there into the cylinder from the exhaust port, which would be, it'd be like an example of reversion. So I've got them both here so you can see what I'm talking about. So you saw me flowing them this way normally. So we have, this is the nail head, the 45 degree, no back cut. Nail head 45 degrees with a 30 degree back cut. And this is the tulip exhaust valve. It only went from 1/10 to 7/10. So you could see the flow as it's going. And you look at the one without the back cut, it will just go across. The one without the back cut's horrible at 1. It's worse than the other 2. Then if I go to the next one, we're looking at 2/10 of valve lift. It's still worse by a bunch. The tulip being second, the 30 degree being the best. Then if I look at 3, it's still worse, with the tulip becoming the best flowing one. And then so on. 4, it's still worse, the tulip being the best, and so on. So you can kind of see what's going on. What you can kind of see by a trend is the tulip for the most part flows the best, except for at the best ones come from right here. So that's the best with the back cut, best with the back cut. And then at 300, it's starting to lose. But at those two numbers right there, the 30 degree back cut's the best. So you think, well, this is your winner. Actually not. Let's look at how they flowed in reverse. So here we have the nail head, no back cut, tulip. Let's see which one flows the best or flows the highest in the reverse direction. In other words, this one would have the most reversion problem. If you said the 30 degree back cut, you're correct. If you look at it, well, right here well, I say that, but the tulip did flow better here. But at any other point, at 200, 107 to 100, and look how low that one was, the nail head without a back cut. Still, and then at 300, way better on reverse flow. And throughout the entire range, if you notice, besides here at 700 inch valve lift, that 30 degree back cut's flowing better in reverse. So what that means is this one, although it looks great here at these numbers, it's the worst for reversion. And this is the reason why I don't put back cuts on exhaust. If they come that way, I will. The only exception to that would be when you've got a really low lift head. In other words, say 400 lift or 450 in some cases for some of the circle track stuff. But otherwise, no. Now, by the way, you might be like, well, what about these numbers up here? Really, if you're looking at overlap, when the two intake and exhaust valves are open, so when reversion would be most likely to occur, it's usually going to happen between 1, 2, and maybe creeping 3. If you've got your valve hanging open at 700 thousandths during reversion, something's off. Or you're hitting the piston, or you must have the deepest valve pockets ever. But anyway, usually during overlap, you're somewhere in this range, 1, 2, 3. So if you look at it from that standpoint, the normal direction, the tulip really is probably the better one. And then if you look at reverse, still 1, 2, 3, the 30-degree nail head's the better at reversion. And the best one at reversion right here would be having no back cut with the nail head. So, but I would rather have, I usually typically use tulip. Now there is an exception to this. With tulips, you have to have an exhaust port bigger because that tulip's taking up space. So hopefully this kind of helps. Now there's another test to go to, and this will be the last one part of this video. I bet you this video ends up being long because of all the cuts together, but I'm trying to give you as much information as possible on this subject. So let's talk about the next thing to test. This is going to be the next thing I test, exhaust pipes. If you notice anything about how I put out flow numbers for my heads and for many other companies, I don't flow it with an exhaust pipe attached, which means I'm flowing it literally just like this. The air just exits. Now some companies like AFR and a few others say, no, I flow it with an exhaust pipe attached. I find that to be the most pointless thing ever, and I'm about to show you why. But anyway, let's get to reasons why I think it's pointless. You're about to see some flow tests and you realize how this doesn't, it makes things look better, but it doesn't really apply. So, but we'll get to that in a minute. But let's just show what we're gonna test. I've got 2 exhaust pipes here. This first one's a 1 7/8, and it's got a bend you would typically see on a header. So maybe it's coming off the head and it might be going this way down towards your frame or something like that. In the S10's case, so I'm gonna flow it in this direction, kind of facing down. Because, you know, if I look at the Camaro's headers here real quick, I mean, we got a pipe that's kind of that way, so we're good. But if I had the S10's headers, you would notice it's not coming off the head this way. It has to go up first because it has to go over steering arm and then come back down. And several headers are that way. But this pipe diameter is 1 7/8, which is typical for a pretty big small block. And I'm probably going to do another video later on about exhaust pipe diameters and different things with those, as far as like why they work and how come you can lose power with a bigger one, which you're about to see some stuff anyway. But anyway, so this is a 1 7/8. This next one, this is a 2 1/8. So it's really, really big, really big. At least for a small block head. For a big block, that'd be about normal. But this is a much bigger pipe, cut in about the same manner. And what I'm gonna do is I'm gonna flow it just like you would expect. So just to recap, I'm gonna take this exhaust pipe, and by the way, it is larger than the head. I'm gonna flow it like this. So I'm gonna flow it, well, you've already seen me flow without. I'll flow it because I got the valve open. I should point out some things. Got the valve open as far as possible, so this should give me the highest exhaust flow. I'm gonna flow it without the pipe, put the pipe on facing this direction. Then I'm gonna turn the pipe and have it facing like this, because some mud bogs guys actually run their headers just like this. That's one. Then I'm gonna take the bigger pipe, same thing, and do the same test. And you're gonna see what's gonna happen. And we'll go over those and why I think it's kind of pointless. But anyway, let's get to flowing. Start off by flowing it, no exhaust pipe. Here we go. My wife's filming, so if it shakes, blame her. All right, now I'm gonna try the exhaust pipe. I'm gonna have her just record this so you can see what's going on, but I'm gonna hold it the down position first. I'll press the record button, hopefully I can reach it, and then I'll do the up position. So there'll be 2 on this, so here we go. Okay, that's kind of a pain. All right, next one on the 2 1/8. Same thing, gonna flow it down, then up. And by the way, the reason why it takes so long, this is the reason why you rarely see me flow with the Super Flow. You can tell how long it takes to spool up to 28 inches. It's frustrating. All right, here we go again. All right, got done. Let me show you the numbers. Let's go to report. Actually, I'm gonna stop this, I'll print it off, and then I'll talk about it so you don't have to glare to deal with. Okay, here's the results. All right, so I'm gonna show you these and I'll talk about them. So this is no exhaust pipes, this first number. Remember, this is wide open, giving it all it's got. This next one's, in other words, the valve's open as far as it can go. The next one's, this is with the 1 7/8 pipe, but I have it facing down. This next one's the 1 7/8 pipe, but I'm facing up. The next one's 2 1/8 inch pipe facing down, and 2 1/8 inch pipe facing up. Now, this kind of emphasizes why I think the flow numbers with an exhaust pipe on the flow bench are just about pointless. I didn't port the head anymore. Look, 252. I could put that out. I'm like, I've got the best exhaust port ever. But remember, this is going on a 355. And it's going to turn 6,000 RPM. You're not going to put a 2 1/8 inch header on it. I don't care if it flows more. You're going to lose power. So this is the reason why I don't do it. We're like, well, other people put it with the 1 7/8, and that's the same. I don't think this engine is going to make the best power with 1 7/8. It's going to even be smaller than that. And guess what? The flow is going to keep going down. And I might say, well, why is that? If it flows more, shouldn't it make more power? Let's go back to the beginning of the video. If you remember what I said, it has to do with the high pressure and low pressure. There's a high pressure area, which will leave a low pressure area on the other side, and that creates a pressure differential causing air to move. That's the reason why we also have wind. Anyway, if you put a big exhaust pipe, you have very little airspeed leaving because it just drops out. So you have no real pressure drop happening because you don't really have a high pressure area or low pressure because it's diffusing all that pressure pretty much with a larger pipe. I'm being over simplifications, but hopefully you can get the idea. Point being is, if it has such a big area it expands to, you're not seeing a high pressure area, which means it can't create a low pressure area behind it for it to draw in more air from the intake valve during overlap. This is the reason why bigger headers typically are not as good down low, because it hurts during overlap. And the reason why they work better when it's at a higher RPM is because now you've got more gases leaving. So although at low speed, it can't create a bigger pressure differential between inside the chamber and then the exhaust pipe. At higher RPM, you've got more gases leaving, so it can add more. Now it has enough gases to fill that space of the larger pipe, creating a low pressure behind it, and it pulls more air in at higher RPM. Now these are in generalizations, by the way, but hopefully you get the idea. The point is, what I'm trying to make by this is the exhaust pipe thing on a flow bench really
is just almost pointless in my opinion. Because say for instance, and I'm not knocking AFR, I'm just using theirs because remember I'm a dealer. I just happen to know theirs. If you go to the website and they say they're flowing a 1 3/4 inch pipe, okay, even if that was the perfect header size for your engine, which way did they flow it? Was it up? Was it down? Because your header may not be that way. Also, then a lot of people see that number from say AFR. I'm just using those for example, and you try to compare it to Brodix, and you're like, AFR exhaust port is so much better. Brodix flows without an exhaust pipe, and you could tell they jump up. Like I gained almost 16 CFM. So point being is, you can't compare the heads that way. You couldn't even compare them if they both had used the exhaust pipe, because how did they flow it? Anyway, hopefully that gives you some better information. This is probably a longer video, and I hope you guys got something out of it. Again, thanks for watching. And this is a long one to produce, so bear with me as this one gets edited, and hopefully everything gets put together right. But I try to give you as much information as I possibly could. If some of it seems like you're just generalizing, somewhat, yes. But this applies to pretty much any engine in A. Which I could do a whole nother video, because this still does apply to boost stuff, because if you don't have enough pressure with the bigger exhaust pipe, it's not going to spool the turbo, which means you're going to have a long turbo lag until you can get some RPM. So, but anyway, this stuff applies to engines using exhaust systems. Maybe not entirely the same way or as much, but they're all applied. Anyway, thanks for watching. Sorry if this is a longer one, but I shouldn't be apologizing. Try to give as much information and cram it in. You guys take care.